Hello everyone, welcome to our Chem 3-4, Unit 3-4 review. This is part of our spring lecture series. My name is Josh. To those of you at the sort of video premiere, welcome. I'll be in the chat. Hello to future me. I will be there to answer any questions. The chat will be open for the 2 hours that this recording goes for. For those of you watching it later on, you're welcome to access that chat. It won't be live, you won't be able to message in it, but all of the messages that were already in there will still be there. My responses will still be there. So if you have any questions, probably good to scroll through that and have a look, because people probably will have the same question during the live premiere, and you can sort of get your answers from there. Other than that, hopefully you're in the right place. This is Chem 3-4. We're going to go through pretty much all of Unit 3, a very brief overview of it, and then a little bit of Unit 4. We're not going to go through sort of spectroscopy or our sort of food chemistry side of things. We're going to go through really all of Unit 3 and then just the organic side of Chem Unit 4. Beyond that, just a bit of a thanks to ATAR Notes. So ATAR Notes run these lectures. They've been running them for a very long time, I think since about 2007. ATAR Notes has a whole bunch of free resources that you can access online. There's free resources such as, the forums. There is the study notes. There's plenty of other things. There's free videos. These lectures, they're all online. All you have to do is go to atarnotes.com.au and you'll find all of that stuff there. We do have some paid resources now, such as TuteSmart, who I sort of work for. That's where I sort of fall into today. That's our sort of tutoring side of things. So we have both one-on-one, private, and a little bit of group tutoring. I mainly do group tutoring. I focus in on Chem 3-4 in my group tutoring. That's the sort of class that I do. But there is also classes for everything else from, English to maths, through to everything else. So you're welcome to check that out. That'll be on the ATAR Notes website as well, for TuteSmart. So today, this is our lecture plan. So our lecture plan today essentially is from topic 1 to 4. We're going to spend half an hour on each. We're not really going to go through sort of exam tips at this point. There are other lectures for that. I sort of go through it in my 1-2 stuff, but I don't really do it in my 3-4 because I feel like at this point of the year, you've probably heard enough of it, and there are specific lectures for that. There'll be lecture series later on that'll cover sort of the exact sort of how to sort of approach exam study, how to, focus on practicing for the exam, how to actually approach the exam, etc. That's the stuff that we'll talk about later on. It's not the stuff we're going to talk about today. Today, we're going to go over a big overview of pretty much everything from topic 1 to 4 here. So we've got thermochem, equilibria, redox, and then organic chem. So half an hour on each, and that is about it. Now, why has that stopped sharing? Give me 1 second. We may have to do a bit of a workaround. Apologies, everyone. You can probably skip forward a minute in the video and I'll have this all up and running. Just have very shoddy internet at the moment. I do apologize, and this somehow has to work through the internet. So you know what we're going to do? We're going to go via cable. Let's go here. And you should be able to see everything. Now, the issue with cable is it doesn't make this thing full screen, which I really don't like. So we're going to make this as big as we possibly can. All right, I think that's about as big as I can make it. I do apologize, everyone. I will try again in a couple of minutes to get the other side of things working. All right, nonetheless. So who am I? Just a little bit about me. So I'm Josh, completed Year 12 in 2018. Reason I'm here, I've got a 44 in Chem, scaled up to about 48, just under, and I take a Chem class at TuteSmart. I've been doing that for about 5 years. I also assist with things such as further and biology. I'm now taking a research year, so I'm a medical student. I am now sort of taking a little bit of an intermission to do a research here at the Victorian Heart Hospital. That should be capital H. That is terrible English from me. And I have 2 very cute pets back in Bendigo. All right, let's move in. So what do you need to know? So what's really important this year, and for all of you, is that you've got to remember that this is what we're looking at. So as much as that says 2021, this has actually been extended all the way through to 2023. Now, for units 1 and 2, they are now doing the older study design. So they're doing the newer study design. So they've changed. They're doing the new study design, whereas all of you are not doing that. You guys are doing the old study design, and it's really important that you get up the right document for that. So this document has been updated. It says 2023 at the top, and it's important that you grab this document. It's important that you've read through this as well. This sort of the way that it words, chemistry-based sort of statements, and the way that it words what you want and what you need to know is really important. So it's really important that you've read through this document and you sort of are focused in on how to use this. Sorry, just jumping across. This is what we've done, and I put these in all of my slides. So if you've been to any of my my lectures before, you will have seen this before. What I do is I've simplified it this a couple of years back now, and I still use it. I simplified down all of the dot points for each of the sort of areas of studies into like their own little topics, and I've essentially gone, look, I've even split it up. I've moved redox from over in area study 1 over to area study 2, sort of in a sense, made these into like 3. Important that you sort of group things together, and then what I've done is I've sort of simplified each of the dot points into what you sort of need to know. So the dot points, you do need to read them. You can't use this as your dot point document, but at the same time, this is a very good starting point. I've also done it for Unit 4, as you can see here. What's really important about Unit 4 is you could probably split this one up into 2. So you could probably split this into, this here, which is like your structures and your properties, and then this as your second part. Analysis is a lot bigger than what has been identified there. Analysis is huge. In all honesty, it's a very, very large topic, and it makes up a very large proportion of everything that we do. So it's important that you sort of understand that moving into your sort of Unit 4 study, is that most of Unit 4 is organic. So most of it is the organic and the analysis. Food chem makes up quite a small portion of that. So we'll jump in. We'll start off with fuels. So what's important about fuels is it's broken into sort of 2 main parts. You have both your fuel choices and your obtaining energy from fuels. So really important, your fuel choices is the memorization side of things. Your obtaining energy from fuels is like your calculation-based part. It's your quantitative information. It's all about sort of how do you actually apply these concepts in a question. So really important, couple of things. I'm going to fly through these slides, so you are not going to have me going through every single dot point. I'm not going to go through every single minute detail of each topic. It's just an overview so that you're sort of refreshing and remembering aspects that you may need to go and study. So starting off with point 1, what is a fuel? You need to know this definition. You need to be able to produce this definition in an exam. You need to be able to go to an exam and say, all right, a fuel is a substance that can be reacted with other substances, leading to the release of energy that can be harnessed for a specific purpose. So you need to be able to do this in an exam. The wording is important. You don't want to say a fuel can be combusted. You need to be able to apply this importantly. It's explicitly stated in the study design. You do need to know this. Fuels, really important. You need to be able to break them up into subcategories. Renewable, non-renewable. I'm hoping at this point in time, you know what these are. So renewable can be replenished. I always like to think of it as a renewable resource can be created quicker than we use it. Non-renewable cannot be created quicker than we use it. Biofuels versus fossil fuels, they kind of just fall into their own categories under renewable and non-renewable. It's pretty sort of straightforward content. So moving forward, we then move into sort of the specific types. So we have, first of all, we're going to go through biogas, then bioethanol, and then I believe biodiesel will be last. So biogas, really important. It's just produced from anaerobic bacteria. That is all you really need to know from this slide. I don't really care about the rest of this stuff here. This is probably important, but whoops. This here is probably important, but you can figure that out from your own, knowledge. You can ask to draw the combustion reaction of methane. That's pretty straightforward. You can do that. The really important point here is that it's produced from anaerobic bacteria decomposition of organic waste. It's important you know that. That's sort of the rote learning part of this that you need to know. So please do know that. And there's a really good point there about why biogas isn't as good as coal seam gas. And that's because, as much as you don't need to know these numbers, but it's a good way of knowledge and it's good application of it. Understanding that CH4 only makes up about 60% of our biogas. We can't really filter it. Gas is quite hard to filter out. It is something that, some places do, but it's really difficult to do. So therefore, we're kind of stuck in this spot of going, all right, well, can't really filter out everything else. So I'm stuck with what I've got, and you only have about 60% of the actual fuel, which is, not as useful as our coal seam gas, which is about 96%. That's why you get less energy from it. Bioethanol produced from the fermentation of glucose by yeast. So again, that's from organic products. So you think of things like barley and wheat. That's what we use for this because they have a lot of glucose in them. You produce ethanol. A really good example of this, and something that's come up in exams before, is that E10 fuel, and then they've got you sort of discuss aspects of that. And it's pretty important to understand that it's 90% your petrodiesel, 10% your bioethanol, and that's why it doesn't produce as much energy, and it's why it's a little bit cheaper. Then biodiesel, I'm sure you know loads about this at this point. Most of you that have just finished off food chem, you will have been through this explicitly as well, that sort of trans-esterification reaction, understanding that you have your fatty acids, you break them off your glycerol using hydrolysis, and then what you get is you are left with this fatty acid with a carboxylic acid that if you combine with a methanol, you can then get biodiesel. Now, a methanol needs to be produced ethically as well, or renewably. That's been a question in the past. You need to be able to source your methanol renewably. If you're not sourcing renewable methanol, then there's no point doing biodiesel. It's not bio because you're not using a renewable methanol. So just another thing that sort of comes up as well. You need to be able to do that as an extra point to build on biodiesel. It's a really good summary. These are really good summary slides. I'm not going to go through these. These are there for you guys and girls to just feel free to look through. Things like your coal, it's like not high yield, but it is. It just comes up. It's one of those things that just randomly put on the exam, and you're sort of sitting there like, damn, wish I'd been through that. So it's one of those things that I say, look, read into your sort of your coal types, your brown and your black, and also knowing that sort of pathway from your coal, from your chemical energy all the way through your electrical energy. There's 5 steps, and you've got the power plant. Really important you sort of know how to do that as well. That does explicitly come up a fair bit. Then you've got, your biodiesel, which is, your fatty acid methyl esters, your FAME, your bioethanol, and your biogas. And these are really, really good summary slides that go through each of those aspects. And I think it'd be great for all of you to sort of have a read through these at some point. So fossil fuels, advantages, high energy content, easy to release energy from, relatively easy to obtain. And this is a really common sense point that is a good one to produce. And sometimes in chemistry, using a common sense point is not a bad thing. Using common sense is sometimes a very good thing. And that advantage is extensive existing infrastructure. Disadvantages are that they're not renewable. We understand that. They emit large amounts of CO2. We also understand that. And they release other toxic chemicals such as nitrogen and sulfur oxides. And their extraction is extremely damaging to the environment. We know all this stuff. If we look further into our biofuels, advantages, they're renewable, they're relatively carbon neutral, so they're CO2, and they're released during combustion, somewhat offset by the CO2 released by the plant to grow, and they burn more cleanly than fossil fuels, so you get less of those harmful like sulfurs and those toxins that we talked about in the last slide. And then if you look on the other side, our disadvantages, again, think of some common sense things here. You're using fertile land to grow crops. That competes with the crops we need, that land we need to grow food crops. Requires large amounts of water to grow crops. These can be quite complicated. These are all sort of common sense things, and I really want to stress that. Sometimes in chemistry, taking a step back and giving a common sense response is more advantageous than giving some very niche technical chemistry-based response. So sometimes you've got to take a step back and think about it from a logical standpoint, and these are some of the examples of that. So, biodiesel versus petrodiesel. So VCAR states in the study design you need to explicitly know this. This has been sort of downgraded for next year, but for all of you, you do need to know this in a fair bit of detail. There's a whole bunch of slides here that sort of go through each of sort of the points. And I think what I did is I sort of got rid of them and I put them into this summary slide. Because I think essentially with this, you all know what you're talking about. I think it's just best that at some point in time over the next, month or two before your exam, you just review this, maybe once or twice, because this stuff is sort of the nuts and bolts of fuels. I'm sure you all know it really well, so I don't need to go through it in super detail, but it is important that you sort of come back to it, give yourself a refresher, go over, what are the differences, why are there differences? So one of them, has a little bit of polarity, one of them doesn't. What does that change? There might be a couple of hydrogen bonds. Those hydrogen bonds make it, more hygroscopic. Leads to things like corrosion, whereas your petrodiesel doesn't do that. It's not hygroscopic, it's got that much reduced viscosity, flows a lot easier, So think about those things before you sort of jump into it. And then there's this one here as well, which I've reused for about 4 or 5 years now, and I really, really like this slide. I think Jack Higgins made this one a few years back, and I really, really like it. It is a great slide in terms of how to answer these questions, because these questions are guaranteed to come up. It's a guarantee that it'll either be, a multiple choice or a 2 or 3 mark question. There'll be something based on biodiesel versus petrodiesel, and if it is a short answer question, knowing how to sort of word it out is really, really important. So like this here, it says, with reference to chemical structure, compare the suitability of biodiesel and petrodiesel as fuels to power vehicles in cold climates. And then you go from there. And I think what's really good is it gives a bad response and a good response. And I think the bad response here, you've got to understand, doesn't talk about biodiesel at all. Yes, we know petrodiesel is the better answer here, but it doesn't discuss why biodiesel is bad. You've got to go into that level of detail. You've got to say, look, whilst biodiesel, has experiences, biodiesel experiences dipole-dipole attractions, petrodiesel only has weaker dispersion. Therefore, petrodiesel has a lower cloud point, lower viscosity, etc. It allows it to, move and flow better with a lower viscosity, and as it's less likely to solidify and clog fuel lines, etc. So you've sort of discussed the differences between the two, and then why one of them is better. And that's really important, because this would be a 2-mark question. So the 2 marks are 1 for the comparison here of the chemical structure, the chemical difference, and then the discussion of why petrodiesel was the better answer. And it's got a really good crescendo at the end. It sort of finishes off with, as it is less likely to solidify and clog fuel lines. It sort of gives that common sense ending to it. So it sort of gives the lay language to it, because all of that language beforehand is very chemistry based, and you're like, ooh, cloud point, dipole, weaker dispersion forces. What is the lay language in that? What is that actually saying? Well, it's saying to the common folk that it's less likely to clog a fuel line. Full stop. That is what you need in the end of your questions there. So there was that. And then we move into things like a little bit more of your application side of things. So we have the universal gas equation. I'm not going to go through this in super detail. All I really want you to know from this is please, 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 please look at your units. You've got kilopascals, you've got liters, you've got moles, you've got moles, you've got this one here is interesting. I don't really stress about the units here. I'm more stressed about knowing the value, 8.314. It is in your data booklet, but please remember it. And then kelvins. Now, remember, kelvins plus 273 on your degrees Celsius. Kilopascals, remember your little table that has, 100 kilopascals, and then it has what are the other values there. So please do know that table. Please know that if you're working with water, for example, particularly water, so water density is another one that's really important to remember. Remember that's 0.987. So what that means is that if I have, I think it's 987 or it's 997, it's one of those two. It's in your data booklet. Nonetheless, what that means is that if you have, 5 kilograms, you don't have 5 liters. That's wrong. You're actually going to have 4.9 something, because you're going to multiply this by this. So really important that you know that stuff. You're not just going to convert willy-nilly. This is really with gases, so you're not really going to be working with H2O gas, but just as a reminder, because we're talking about units. So I just wanted to sort of remind you all, even though this is working with gases. So really key point, pay attention to your units. Remember your molar volumes. There has been questions in the past explaining why we use this. Remember that it's SLC, and at SLC we have 100 kilopascals. We have 1 molar, which isn't as useful because this is with gases. 1 molar is more with your solutions. And we have 25 degrees Celsius, which is 298 Kelvin. So if you go and put that into your equation where you have volume equals N times 8.314 times N times 8.314 times 298 over 100 kilopascals, you end up with an answer of 24.8, and then you have like V equals N times 24.8, and that's what you end up with. So really important. That's sort of how we work through that one there. So as it says there as well, in the ulcer design, it was 24.5. That's actually probably a really relevant point for all of you. If you're working with older exams and you see a question and you do it and you get it wrong, and then it's like because it used 24.5 or it used different values, that's because in the older exams, SLC was slightly different. So please just note that. I think it's from about 2013 down. You'll find that. Your answer is now correct. Their answer is now wrong, but back in the day, their answer was what it was, so you just need to be aware of that. And the formula data book looks a little bit like that there. All right, so to compare, so if we move on, to compare the amounts of energy released to absorb in a system, we use the concept of enthalpy of change. Enthalpy of change is delta H. Remember that delta H, if it's less than 0, it's going to be exothermic. Now, you do need to be able to draw it on these graphs. It's important you don't draw it like this. Remember that we're going to draw it like this. So that's your exothermic one. Remember that this here is your delta H, and that this in here is plus this is your total sort of energy change. Important that this individual line down here is just going to be, sorry, this is your delta H, sorry. Don't know why I said the other one at the top. This one at the top here is your activation energy. Mind my little error there. Activation, and when you add the two together, it's just sort of total energy change from top to bottom. If you add the two together as well, it's your delta H, your backwards reaction. So, not your delta H, your activation energy. I always get these concepts mixed up. Activation energy, all the way at the top. Delta H, your change. So that's how that goes there. Remember that if it's the other way around, you need to be, I keep doing this. I keep knocking the button when I go to put my arm on it. Do apologize. But this one here goes a little bit like this. Again, this here is your activation energy, and your delta H is still this, but remember it's now gone the opposite way, so it's going to be positive. Some really good common examples as well is like, your methane combustion or any combustion. This one here is a good example is your photosynthesis. This equation tends to come up a lot more than you think. It's not explicitly part of the study design, but it's one of those ones that I sort of say to my students you probably should know because they do like to bring it up. So I would suggest, having a read through that and knowing your photosynthesis pretty well because it does tend to come up. It is explicitly more part of the study design from next year, which obviously doesn't affect you now, but at the same time, sort of good to know. Now, really important, the thermochemical equation is made up of two parts. It has the equation that has the delta H. Really important, if it's a thermochemical equation, it needs to have a positive or negative for your delta H. Even if it's a positive number, it needs to be positive, and you also need to multiply it by the fuel. So in this one, you're working with ethane, but when you do an ethane combustion reaction, complete combustion, you use 2 at the front of here. To balance it out, you have to have a 2. Please do not use halves. Please don't use fractions. I know they do accept it, but it doesn't look good, and you'll find as you go further up into chemistry, we don't use fractions on our chemical equations, especially at like university level, because you don't have fractions of chemicals. Really important. It's like saying half a human. You don't have half a human. It's not a thing. You don't have half a chemical. You have a full chemical. So please do not use fractions of chemicals. If you have a fraction, usually it'll be a half. Make sure you double it, or you'll have like 5/2 or whatever it is. Double it. Please just double it to get it to a full number. Make sure you have whole numbers all the way through. Because if in this one here, essentially if you balanced it, you would have had nothing there. You would have had 3.5, which would have been, 7/2 or 3.5. you would have had 2, and you would have had 3. Really important in this case here, you just had to double it. You had to double in this case here. And they have. In this question as well, when this is doubled, when the fuel is doubled, this needs to be doubled, which it is, because if you go into your data booklet right now, you would find that, I believe I actually have my data booklet up if I scroll across. Sorry, wrong one. If I go to here and I look in my data booklet and I find my fuels are a bit further down, apologies. Where are we? We're past here. Yeah, if I find my fuel here and I find ethane, ethane is 1560 kilojoules per mole. This is double that. What I've got on my screen here is I've got double that. So this has been doubled because this has been doubled. So important. Don't forget your sign. Now, really important, you also need to know how to manipulate your thermochemical equations. Here's just a few really good examples of how you work with it. If you're going to double, again, as we've already discussed, you're going to then double your delta H multiplied by 3, multiplied by your delta H by 3, etc. You're going to flip your equation. You're just going to flip the sign. So it's just going to go from positive to negative. It's just like the back reaction. Think of it like this. That's a terrible little drawing, but if you're going this way, then that's going to be your delta H going down. But if you're going this way, your delta H is going to be this going up. So therefore you're going to have positive. It's just going to change. And also know that if you divide, you're going to divide as well, etc. All that sort of stuff. Also know that if you add equations together, you're going to add them. So it makes sense. You're going to go ahead and add the delta H's together, and therefore you're going to have a different delta H at the end. And we already showed you this, but this is in the data book at page 10. Please do know where this is. Now, what's really important here as well is in the wording. Notice how there's no signs on this. There's no signs here. These are all reported as positive values. So these are all positive, but these are really importantly are different. These are heats of combustion. These are not enthalpy, so our change. These are heats of combustion. So these are what we refer to as delta HC. When they are a heat of combustion, delta HC, they do not have a symbol. So delta HC of ethanol is 1,360 kilojoules per mole. However, you are never going to put a delta HC, or a heat of combustion, on a thermochemical equation. On a thermochemical equation, you are always going to have, if I go back, you are always going to have, keep going back, God, so far, you're always going to have an enthalpy of change, or a heat of reaction. Enthalpy of change, heat of reaction, that is a delta H. That requires a symbol, as you can see on this. A delta HC is a heat of combustion, and it does not have a symbol. It is assumed positive because it's just showing how much energy there is either released or absorbed. Doesn't discuss that side of things. It's just your delta H. So delta HC, so heat of combustion. So really key point when running a thermochemical equation under SLC conditions, water should technically be shown as a liquid state. That's also another thing as well. It's one of those things that just need to keep an eye on. But it's also, if everything else is a gas, sometimes you can get away with having a liquid as a gas. So if you're working with things like ethanol, not ethanol, sorry, like methane or ethane, usually they're a gas, so you can sort of get away with using those, the water as a gas. So as you can see here, delta H versus delta HC, this is very sort of niche stuff, but it's sort of the stuff I want you to start practicing now because you're getting close to that point of, you know, practicing exams and working on the little niche things. And then calorimetry, you guys have been through this in sort of the last couple of weeks, I'm assuming, with food chem. But just to quickly revise calorimetry, you need to know your Q equals MC delta T. This does come up in fuels as well. But remember that we're working with joules and the Q equals MC delta T. Remember that our specific heat capacity of water is 4.18. It's the only one you need to know. All the other ones will be given to you if you use anything else. Massive substances in grams. It's not a volume. So this is another one where you usually get given a sort of a mils and you need to convert it to grams. And then you've got to change the temperature of the substance. It can either be delta H, it can either be a degrees Celsius or Kelvin here, doesn't matter because the change in temperature from 25 degrees to 30 degrees compared with the change in temperature of 298 to 302 or 303 Kelvin is much of a muchness. They're going to be the exact same difference. There's also some more calorimetry equations here, which you've all been through, so I'm not going to go in detail and cover those ones now. But if you need a refresher on this stuff, go to sort of Unit 4, Area Study 2 content. They do this much better there. They sort of cover this in a lot more detail, and they do a much better job of it. And it's one of those things that you just need to be able to apply in those situations there. All right, so that's everything to do with fuels. For those of you who are there at the live premiere with me, any more fuels questions, get them out now so that I can answer those fuels questions now. And then we're going to jump into our second topic. And we're about smack bang on time. I think we're about 31 minutes, 31 or 32 minutes. So very good. Rates and equilibria. So again, we can break our rates and equilibria. Equilibrium. I think that's actually spelt wrong there. I do apologize. We can break it into reaction rates and equilibrium. Reaction rates is very small though. Reaction rates is very easy and quick to go through. Essentially, it's sort of like your process of speeding up a reaction. Equilibria is where things actually get quite difficult and you need to be able to apply your knowledge in a pretty straightforward sense. So let's have a look at two things. Let's look at, first of all, collision theory. So collision theory is part of our rate side of things. So collision theory is essentially the understanding of how do I make a collision successful? How do I actually get what I want out of it? So there are two main aspects. You need to have a sufficient energy available in your collision, and you need to sort of have that collision occur at correct orientation. So there are two things that you need out of this reaction. So first of all, collisions must have sufficient energy. That is just your activation energy that we're talking about. So a much better diagram than what I was drawing before, and it's not going to have any errors like I was doing before. You're going to have your activation energy there. You just need to have that amount of energy available when your collision occurs for this reaction to actually get done. For the collision to also occur, you need the correct orientation. This is where you need something to knock it in the right place. So as you can see, you don't want to knock the direct molecule that you have or the atom off. So you're not trying to hit the actual atom that you want knocked off. You need to hit the other side. You need to hit the atom that you want to connect to. So in this case here, your hydroxide group needs to hit your carbon and knock your bromide group off from the other side. If it hits the bromide group, nothing's going to happen. That bond is much stronger, so it's already going to stay, and it's going to stay there and do its thing. So rates of reactions. We are also concerned with making reactions go faster. What can we do? There are two fundamental ways. So first of all is to increase the number of collisions, and then second of all is to increase the number of collisions that are successful. So first of all, increase collision frequency. There are three things there. Increase the proportion of successful collisions. There is another two things there. So how do we go through each of these? So method one is to increase the number of collisions. So first of all, increase the temperature. This is just shows the steps of how these work. It's pretty straightforward sort of stuff. I think you'll all be fine with it, but you're going to have a higher temperature, so molecules are going to move faster. You're going to have more collisions occurring. Think of people running around in a small room. You're going to have a high frequency of successful collisions, etc. More particles, more collisions, so more successful collisions. Like you just have more particles, it's going to be more collisions. Think of it like a metro train. You're on a metro train with only a couple of people, not going to matter. You're on a metro train. After a footy final, you're going to have heaps of people. You're going to be running into people all the time. Increase surface area. If there's more surface area for things to bump into, so if you're working with a solid and there's more surface area, so maybe you make it into a powder rather than having a big blob. So let's just say you have an acid or you have something, you have a solution and you want to dissolve something into that solution or react something into that solution. If you make that a powder, it's going to react a lot quicker than if you have a big solid lump. It's going to take a lot longer. Then second method is to increase the proportion of successful collisions. The one that goes over both of these is temperature. If you increase the temperature, well, you're going to have more sort of kinetic energy available. With more kinetic energy available, or energy in general available, you're going to have a greater opportunity to get over that activation energy, and therefore you're going to have more proportion of successful collisions. if you use a catalyst as well, this is sort of the other way of doing it. You lower that activation energy, and therefore you don't really need more energy because you just don't need as much, and it's still going to work. So if I look at this here, just 2 quick points on this. As you can see here, this is sort of your catalyst. It's important you know how to draw one of these out and discuss that, hey, this was the original activation energy as it's shown here, and then this is the new activation energy. It's important you know how to draw that out and discuss that. That does come up quite frequently, and it is an expectation that you know how to sort of discuss that. So summarize, these are the 5 main factors. As I said, it's taken us like nearly not even 5 minutes to go through this. This is pretty straightforward sort of content. You just need to be able to apply this in a question. All right, then moving on just quickly before we get into equilibrize the Maxwell-Boltzmann curve. This is a really good way of sort of picturing what's going on. So think of this as a curve that all the particles fall under the curve. So the area under the curve, the area under this, the shape is all the particles. And if you put the activation energy at some point, so let's just say the activation energy, this is sort of like the energy on the x-axis that they contain. If you say the activation energy is like, 2.5, is like here, that's like 2.5. It's not a very good line, but close enough. All the particles in this area here are the ones that have enough energy to get over, if they collide, they're going to have enough energy to get over the activation energy. You could say that there is like 15%. Therefore, the other 75%, which if I use a different color, the other 75% in here, the other 75% cannot get through. So they're not strong enough to be able to get through. And therefore, you're going to have this issue where your activation energy, where these don't have sufficient energy to get over the activation energy. So this is actually a really good meme for once. It's a meme that actually sort of describes what's going on and what you need to know. So the first 2 here are wrong. If you're going to increase your temperature on your Maxwell-Boltzmann curve, so this is your Maxwell-Boltzmann curve, this is your activation energy. If I increase my temperature, what you actually do is you flatten the curve. You flatten it out a bit like this. The activation energy stays in the same place. So the activation energy is still here. That's still the activation energy. But now, instead of having this much being able to react, because you've increased the temperature, you've got an increased amount of kinetic energy available. There's more energy in the system. This is now what reacts. So this is now what is going to be able to react and what is going to, work. So as you can see here, this is your example that works really well. So that's what happens. None of the other 2 there happen. You don't just shift the whole curve over, you flatten it. You don't just increase the number of particles, that just increases the number of particles. That's wrong. You are flattening the curve and pushing it more to the right in a sense. If you add a catalyst, you just don't change the shape. So adding a catalyst, the biggest hint is you do not change the shape of the Maxwell-Boltzmann curve. It stays the same. You just move the marker where the activation energy is. So you move this marker from this point here to this point here. Therefore, instead of having this, you now have this. So you have a much higher proportion of successful collisions, and that's how a catalyst works. So Maxwell-Boltzmann curve is a really good way of visualizing what goes on to increase reaction rate, and I actually really like Maxwell-Boltzmann curves for that reason, the reason that they sort of show you really nicely how these things work. So rate of reaction versus extent of reaction. This is where we sort of phase in from reaction rates into our next phase, which is sort of our sort of equilibria. So reaction rates, so these are how fast the reaction occurs. We've discussed this. We've sort of, how do we speed it up? How do we make things go quicker? Because we always want things to go quicker. Now what we're going to move into is the extent of the reaction. So how far the reaction has gone. How can we make the reaction go further? How can we get more yield? We can get more of what we want. So please don't mix these 2 things up. You need to be able to discuss sort of yield versus rate. So this is where we get into equilibrium. As I said before, I definitely spelled that wrong with the B and the R. I apologize. Equilibrium. the forward and reverse reactions exactly cancel each other out. So this is when we've reached equilibrium. And to get more yield, we need to move equilibriums, and we'll discuss that in a little bit. But this is probably the best GIF that you'll ever get to describe what is going on in an equilibrium. So this GIF describes that we have, reaction, we have our reactants, we have our products, we have our start and our end, we have our forward and our back. Our forward and back reaction here are occurring at the exact same rate. So it doesn't look like there is any change at all in the forward and back reaction. There is no change at all. As these ants go from one to the next, there is no change in our forward and back reaction. There's no change in how much reactants and how much products we have. They stay the exact same. So it looks like nothing is happening. So if you look at just the amount of reactants and the amount of products, it looks like nothing's happening. In actual fact, there is still the reaction going on. It just appears like nothing is happening. And that is why we call it a dynamic equilibrium. And it's something you do need to be able to define. You need to be able to define what a dynamic equilibrium is. And what you're saying is that the forward and back reactions are occurring at the exact same rate, and therefore it appears like nothing is happening. Something you do need to be able to describe. No reaction appears to occur because the forward and reverse reactions occur exactly the same rate, meaning the amount of each doesn't change. So this is sort of what it looks like in terms of rate. You start out, so in this one here, you'll have started out with a lot of products and no reactants. And as you form reactants, the products sort of reduce and the reactants increase, but the reactants start reacting to form back into products. And so you get this reverse reaction increasing. And once they meet in the middle, you are at equilibrium. That is what we call our sort of perfect equilibrium. Now, give me one second. I'm just going to move this here to give me more shadow. That is a lot better. I can now, apologies, do what I was doing without getting burned by the sun. So continuing on, our amount or our concentration, you'll find these as concentration time graphs. So this is what we refer to as a rate time graph. So this is a rate by time graph. This here is a concentration. It says amount, but we're going to say concentration. Concentration by time graph. So these are different. So we have rate by time graph, we have concentration by time graph. These are distinctly different, really important. So as you can see there, we reach equilibrium at this point here where there is no change. So equilibrium, no change in the amounts. So that is what it is. So when we reach that point, there's no change, we move on. And that is when we're at equilibrium. So really good way of picturing it. Here you've got N2 and O2. You've just put those two gases in. You've put no NO gas in. When we reach equilibrium, we've got a bit of both. Now, it doesn't necessarily need to be equal. We don't have equal amounts here. We have a little bit of difference. That's because all equilibriums are different. Some of them like to finish with lots of one part, and a lot of them like to finish with none of some of it. So what I'm trying to say there is if you think of equilibrium like a sort of spectrum, like this. And at this end, we have 100% reactants. At this point here, we're at 50-50 split. And at this point here, we have 100% products. Equilibriums can stop at any point along this. Now, each type of reaction with the same condition, so the same temperature, the same sort of environment, pressure, all that sort of stuff. Keeping those things the same, you're going to get the same position of equilibrium. So you might get like a 70-30 split. And it will be the same no matter what you do with that. So as long as it's the same type of reaction at the same temperature, no matter what you do with that, you're going to get the same sort of split. If you change the temperature, it's going to change. If you change what the reaction is, so you go and use a different reaction, you're going to get a different point. You might get, 40-60 instead. So your splits are always going to be different for each type of reaction or the same reaction with a different temperature. And that's the most important aspect that you can get out of this here. So moving forward, we sort of describe this with our K value, and I'm sure you all know your K value well at this point. Your K value is super duper important to understand how it operates. So we have two K values below. We have one that is really, really small, negative 31, and we have one that's really, really big, 10 to the 19. What does each of those mean? Well, the 10 to the negative 31 tells me that I have lots of reactants. Lots of reactants. So if I we'll draw out this spectrum again, sorry, and this is our, remember, this is our 100% reactants, and this is our 100% products. This equation here, which if I go, I'll put this one in orange, so this is this equation here, is going to be all the way down here. It's going to be really low. Whereas this one here, which I'll do in green, is going to be all the way up here, because this one here is going to have lots of products. Now, how do I know that? That's because I know products is on top of reactants in my K value. So when my K value is really big, this value needs to be really big, and this value needs to be really small. When my K value is really small, I need this to be really small, and I need this to be really big. I also should have some green so that it sort of matches out with my colors. So that is what I'm trying to display there. That is how that there works. So really important that you know how that operates. Now, looking at this equilibrium constant again. So this is the actual formula. Now, really important with this formula, I'm hoping there's sort of an example. Do I have an example in here? I have this question, but I don't have any examples. All right, we will jump back. So jumping into this, really, really important. This here must be written out, but I don't want you to write it out with A, B, C, and D. I want you to write it out with the actual whatever it is. So in this last question, we had this here. We had, we'll use the green one at the bottom. What I want you to write out is if you're given all the values and you're asked to formulate, to give a K value, you're going to go K equals, and the first thing you're going to do is you're going to go, all right, HBr2 over H2 multiplied by Br2. Really important. That's the first thing you're going to do. You're going to write it out like that. And you are going to put that on your page. That's the first thing that you're going to do with these questions. Now, even if it's a 1-mark question, this is not necessarily worth a mark. But most of the time, these are 2-mark questions, and that is worth a mark. Writing out that formula there is worth a mark. Really important that you do that. So, as you can see here, this is how it's written. You don't need to put in the little EQMs. That's a bit useless, and just saying here that that's an equilibrium. So remember that a K value depends on the starting conditions of the reaction. However, K does depend on the reaction temperature. So it doesn't depend on anything else. It just depends on, 1, what is your reaction? So what are you actually reacting? And then 2, the temperature. They're the only 2 things that change your equilibrium constant. Otherwise, if you're working with the exact same reaction, just different conditions, volume, etc., you are going to have the exact same K value. So temperature is the only thing that can change the K value. In this sense here, if I increased the temperature of this equilibrium, we're going to go into this in a little bit more detail with Le Chatelier's, but if you think about it, this is a exothermic reaction. Exothermic reactions release heat. So when they release heat, I'm going to think of this side as hot. So if I do the forward reaction, I'm going to release heat, I'm going to be really hot. If I do the back reaction, I'm going to be really cold because I'm going to absorb energy. So if I go backwards, I'm going to do an endothermic reaction, I'm going to absorb energy, I'm going to be really cold. So what is the effect of an increase in temperature on the equilibrium constant? Well, if I'm going to increase the temperature of this whole thing, so I'm going to increase the temp of the whole reaction, what am I going to want to do? I'm going to want to cool down. So I'm going to want to cool. So to cool off, I'm going to go backwards. So I'm going to force this reaction backwards. By forcing this reaction backwards, what do? I increase my reactance. And increasing reactance will reduce K. So as it says here, system wants to reduce temperature. It favors the endothermic reaction. Therefore, there is more reactance. You're going to reduce K. So it says here, exothermic, endothermic. So an exothermic reaction, if you increase temperature, you reduce K. If you reduce temperature, you increase K. It's the opposite for endothermic. So I don't like to usually look at both of these. I usually like to scribble one of these out like that. And I usually just like to look at one. If I look at two, it just confuses me. Using one is really useful because I can say, all right, exothermic, if I increase temperature, reduce K, reduce temperature, increase K. Pretty nice to think about. So reverse reactions. So this is how you also manipulate K. So if I reverse the reaction, I'm going to flip my K value. It makes sense because I flip my A, B's, C's, and D's. As you can see there, I put my A and B on the top because it now becomes the product because I flip my reaction. So 1 over K. If I double my reaction, I'm just going to square my K value because I'm now going to add a little square to all of my values. If I'm going to what do you call it? Divide, sorry, my my equation, or in this case it's halved, I'm going to square root, or cube root if I divide it by 3, etc. That's how you go about that. Now, quick little difference that you need to know. What is the difference between my K and my Q values? Remember that Q values are your reactant quotient. K is your equilibrium quotient. What does that mean? Q is when the reaction is sort of, if you think about it, that Q is your value when your reaction is not at equilibrium, and K is your value when you are at equilibrium. So Q and K are the same thing at equilibrium, but you're going to call it a K value because you are at equilibrium. If you're not at equilibrium, you're going to call it a Q value, and that means that a Q value can change. So Q value is going to show what my reaction needs to do to get to equilibrium. So Q is less than K. You're going to increase the products because Q is a smaller value. You need to increase the products which are on top, and it's going to shift. So it needs more products. It's going to shift to the right. If your Q is more than K, you're going to want, you've got too many products, you're going to want more reactants. And so therefore you're going to shift to the left to get more reactants. And that's what it described in these two. I said it the wrong way around, but that's what these two dot points here describes. And it's important you sort of understand those two products. Now, if Q is equal to K, we are at equilibrium and there is no change. And that's really important. So Q is equal to K, we are at equilibrium and there is no change. Now, this is a really good practice question. It's one that comes up quite frequently in sort of practice papers because it was one of the most poorly answered questions of all time in an exam. So it's really important, I think, that everyone has a go at this question. So what I want is for everyone to sort of pause the video right now if you're sort of, watching the recording, or if you are not watching the recording, you're in the live premiere, I think you can still pause it. Do feel free to pause it, and then we're going to go through this question straight after you sort of restart. So I'll give you 3, 2, 1, pause the video, and then welcome back. Let's go through this question here. So what we've got is the concentration of reactants and products we're studying in the following reaction. This is at 25 degrees. In an experiment, the initial concentration of gases were and When the reaction reaches equilibrium at 25 degrees, the concentration of HF will be. All right, so really important. You've been told nothing about the values at equilibrium. You've just been told what they are at the start. So let's start off. Now, this is multiple choice, so you don't need to do all your workings, but I think it's better to do them all. So we're going to have HF squared over H2 multiplied by F2, which is 0. Oh, I need to write out F2, sorry. Then you can go ahead and write out your values one if you want. So I'm going to write out 0.4 squared over 0.02 multiplied by 0.01. Now, because I don't have a CAD calculator on me, I'm going to be using or like a Casio, I'm going to be using my iPhone, so it's not going to be as useful. So I'm just going to have to write things out as I go. Apologies. 0.002. All right, and then I have 0.4. And then I divide that by 0.0002. And the value of K equals 800. Now, really important, I made a little error here, and I do apologize for that. This is not K. What is this? This is Q. So Q equals 800. So from this, what I can say is Q is greater than K. What does that mean? When Q is greater than K, when Q is greater than K, I need to increase my reactants, or do I need to increase my products? I need to increase my reactants. To increase my reactants, I need to reduce products. So if I look at my value here, I was given HF is 0.4. If I want to say that at equilibrium, is it going to be 0.4? Well, no, this is what I initially had. It's going to change. It needs to reduce, so it's not going to be a bigger number at equilibrium. It needs to reduce, so it's not going to be a bigger number at equilibrium. I'm left with the answer D, less than 0.4 molar. That's really important because it needs to reduce. You cannot figure out what the actual value is. You just need to know that it needs to reduce. So this is a really good multiple choice question. It's from ages ago. This is how useful some of these older exams are. Yes, there is a lot of stuff that is useless, but there is still a lot of stuff in these exams that is quite useful and is really applicable to what you're going to be doing. So you need to have the time in the year to actually spend a bit of time on these older exams and, have a look at what's going on. So, awesome. This sort of shows what I just did. Shifts to the left, your answer is D, etc. So moving on, the Chatillon's principle, you do need to know this. You do need to be able to define it. It is one of the ones that you must be able to define in an exam, so please do know this. I'm not going to go through it in any more detail than that. What's really also important, let me just go through Rice tables, that's it. All right. What's also really important as well is just understanding it's something that we didn't put in here because we probably didn't, I'll be honest, I probably cut it because of time, is just understanding how, with Le Chatillon's principle, those changes to your concentration times graphs. So, if you have here, and then let's say we increase this one, and let's just say this is 2 factor, this is 1 factor, these are the molar ratios. Remember that this is going to go down, and when it goes down and reaches equilibrium again, it's always going to be higher than this point here. So we've added some here, and it's always going to be higher than this point here. Really important. It's never going to reach that line again. Now, how much does this increase by? Well, this is going to increase by, if I go like this area here is going to be half of this here. So this is going to be like, 1 centimeter. It's not really, but just for common sake. And this is going to be 2 centimeters because this is a factor of 2. So this change from this point here to there is double compared to this point here to this point there, which is half because of our ratios. That is the use of Le Chatillon's. Remember Le Chatillon's, you need to describe things like, if I change pressure, which way is it going to go? Well, it's going to go to the side that has less particles or more particles, depending on if I increase or reduce, all that sort of stuff. So important you understand those little concepts going into equilibrium questions. So, lastly, numerical equilibrium problems. Example, calculate the final equilibrium concentration. You need to be able to use ICE tables, or some people like to call them Rice tables. Rice tables essentially stand for ratio and then initial change equilibrium. I usually use ICE tables and then have that top line and just don't put an R in. I like ICE tables better. But if you use Rice tables, go for it. They're the exact same thing. Really important you understand how to apply your knowledge in these. So we'll go through an example. You have a question here. We have initially this, and this, and you're sealed in a 1 liter container, and you end up with this. So, Rice table. So, a line, and a line, and we're going to have CO3H2. We're going to have CH4. And we're going to have H2O. So therefore, we're going to start off with 0.1 molar because it's 1 liter. I'm going to divide all of these by 1, so it's just going to be the same thing. 0.2 molar. Now, you can do this in moles. You are welcome to do this in moles. It's the same thing, but you will need to change it to molar at the end. So if that had been like, 2.5 or something, an ugly number, I would have done it at the end, but easier while I go through. And then I end up with, at equilibrium, I end up with 0.032 molar, which is, it's a bit of an ugly number, I'll be honest, already. But essentially what's happened here is we've lost 0.78, I believe that is, just confirming. 0.1 take 0.78. Wait, 0.1 take 0.78. No, 0.078, sorry. There's an extra 0 in there. 0.01, okay. 0.1 take 0.078. 0.068. Sorry, I'm having an absolute mind blank right now. 0.1 take 0.068. Good to say we're not in a maths lecture right now. So nonetheless, that is what we've done. That is at a 1 ratio. So therefore, this is going to be exactly the same. And this is going to be 0.232 molar. And then over here, we're going to be adding. So these are both going to be add and add because they're on the opposite side. So in this case here, 1 ratio, 0.068. I'm going to end up with 0.168 molar. And then here, I'm going to be adding 3 times that. So 0.068 times by 3 is 0.204. So I'm going to end up with an answer of 0.404 molar. And that is our final answers in our RICE table. So as you can see there, that is what we get. And I think all our answers lined up pretty well. So that's how we do that question there. So really important, you know how to utilize these tables and you get the simple arithmetic right and you use a calculator that's not an iPhone. Please practice on your Casio calculators, not your Casio class pads, your proper Casio little ones. All right. I think we're about an hour and 3 or 4 minutes in. So we're pretty much on time. We're probably a tiny bit behind. That's okay. We will fly through it. The organic side of things, there's not a lot. So usually this lecture takes about an hour 55. So I think we're about right on track. Those of you who are watching the recording, if you are struggling at this point, getting a little bit distracted, you pick up your phone and whatever, please take a break, pause, take a 5-10 minute break, go to the toilet, have a drink, whatever. Please make sure you sort of get yourself refreshed to focus back in. Those of you at the premiere, also feel free to do the same thing, but try and catch up as you go along. Let's jump into our topic 3. So we're up to redox. So the fun side of things, we all love redox. No, we don't. Redox is a pain, and it's just, I think what's really important about redox is you understand the basics. You need to make sure you have a really sound base to go off. If you don't have a sound base to go off, you're really going to struggle in redox. So let's go through sort of that sound base. So understanding your oil rig, oxidation involves loss of electrons, reduction involves gain of electrons. Really, really key point. Just the most basic side of things with redox is understanding those points there. Oxidation involves loss, reduction involves gain. Just understanding that will put you in a much better place. Also, having really strong knowledge of your terminology, oxidant versus reductant. Now, this can be super confusing and can confuse the most strong students, the ones that get really high marks, they still get confused by this. So having a really strong understanding of just the terminology of this. The oxidant causes oxidation and is itself reduced. The reductant causes reduction and is itself oxidized. So the oxidant doesn't actually go through oxidation itself. It causes something else to go through oxidation. Because we are paired as a backhand back, you are going to then go through reduction. So the oxidant, because it causes oxidation on the other side, ends up itself being reduced. The reductant, on the other hand, because it causes something to go through reduction, it then itself gets oxidized. So think about it as the oxidant causes the reductant to be oxidized. So the oxidant goes, you need to be oxidized, and it causes this thing to be oxidized. Then this goes, you need to be reduced. So it causes this to be reduced. So sort of works like that, and sort of knock on for each other, and it's a pairing. It's a bit like how the teacher does the teaching. They don't themselves be taught, they do the teaching. So Oxidation states. So if we look at this here, how do we determine which of these is redox? This is really the basics, but it's the basics that you need to have a really solid understanding of, and that's why I like going through this. We need to use oxidation numbers and oxidation states. Please have a sound understanding of the rules of oxidation states and how you sort of go through them. So please make sure you know, hey, first of all, oxidation states are free elements. I'm going to go, they're all 0. Please understand that oxidation states of simple ions are, +1, -1, +2, -3. In compounds, your main group metals have oxidation states equal to the charge of their ions, +1, +2, etc. Hydrogen is almost always +1, and oxygen is almost always -2. Now, there's only one example that has come up for those two, that is for oxygen, and that example is H2O2, which is hydrogen peroxide, a dangerous molecule. Hydrogen peroxide, in this one, this is +1, which, overall is +2. This is -1, and so overall is -2. It's a poison in a sense, hydrogen peroxide, because the oxygen is so unstable. The oxygen hates being in that -1 state, so it itself is really, really unstable and isn't happy, and therefore you get this reaction. You get this unstableness, and you get this dangerous molecule, which ends up being a poison. So hydrogen peroxide is the one example that has come up in exams of where oxygen is different. I've never seen an example of hydrogen being different in an exam. I've seen examples of it online, but never in a VCAR exam have I seen an example where hydrogen is different. It is always +1. Oxygen, on the other hand, has been different with H2O2, but never with anything else. Otherwise, it's always -2. And then understanding how the sum of all oxidation states must equal the charge of the species. That stuff is the basics. You should know how to do this at this point of the year. If you don't, please work through this, get some molecules up and just do this. Figure out what they are at the top, and then do the maths at the bottom to make sure it solves out. All of that. So please just practice this if you struggle with this, because this is your nuts and bolts. This is your basics. This is your cement slab to your house. Being your chemistry knowledge, you need to know this. So if you look at this example here, which of these is oxidation? The first one is not. Or which of these is redox? Sorry, the first one is not because the numbers stay the same. The second one is not because the numbers stay the same. The third one is because we have a change in oxidation states. So for redox to occur, you need a change in oxidation states. This indicates that there's been a movement of electrons. So as much as it's easy to say, oh, look, oxidation states, therefore, so because there's been, a change in oxidation state, we have redox. But why? That's because there's been movement of electrons, and that is what is essentially redox. Redox is the movement of electrons. It's electrons going from one thing to another, and that is essentially what is happening here. We've had a change in electrons. If the oxidation state reduces, then all species all the species was reduced. So Cl goes from 0 to -1. If the oxidation state increases, then that species was oxidized. So Al goes from 0 to +3. So think about that as oxidation involves loss. Oil rig, oxidation involves loss. Loss of electrons is loss of negative charges. Therefore, it's going to become more positive. That's one of those things that even confuses students still, is understanding that if you lose electrons, you're actually going to gain charge. So losing something that's negative is going to make you more positive. Losing something that is, and then gaining something that is more negative, even though you're gaining, you're going to become more negative. So important to understand. Also, understanding your Coe's method of making a half equation is really important. If you don't use this method and you have a different one, please stick with it. If you don't have a method at all, please use the Coe's method. The Coe's method is essentially a 5-step process to writing out a half equation. So I'm hoping there's sort of an example. There isn't an example, but if you had an example of, changing something to something else. So I think a good example is I can't think of one off the top of my head, but there's usually an mn something goes to, MnO4. I think there might be a negative in there. Anyway, I don't remember it off the top of my head, but that's the example. It's like Mn2 or something. I don't remember off the top of my head. Nonetheless, with this one, essentially, if you just think of it like this, you need to balance your key atoms. First of all, you're going to balance these. So there's 2 of these, so you can put a 2 there. Then you go ahead and balance your oxygens. There's 4 here, so you're going to add 4 H2Os. Then you're going to balance your hydrogens. Well, you now have 8, and you have none, so you're going to add 8 H pluses. So now you've got a charge of nothing. You've got a charge of +7, so therefore you're going to add 7 electrons to this side to balance out your charges. That's how you balance out that equation there. Now, this is a terrible example because I don't actually think it's a real example, but nonetheless, I'm just trying to show you that's how you use the Coase method, and then lastly, you add states. I didn't there, but you're really important. That is sort of just cleaning up your answers. That's just exam technique, is remembering you need to have states on everything. So that's exam technique. That's stuff you need to practice when you do practice exams. So when using the Coase method, we have been making an assumption that the reaction medium is acidic as well, is also sort of the next point on. So remembering that this as H pluses. H pluses, in a sense, reduce your pH, and therefore you are in an acidic environment. This is acidity. If you're going to use that method, you are assuming we are acidic. That is the basis of it. We are assuming that we are acidic by using that method. What if we were told we're in a basic environment? If we're told we're in a basic environment, we add an extra step. We add in adding of OH ions. Now, you add as many OH ions as you have H plus ions to that side, and you add the same amount to the other side. So in this one back here, I got rid of it, but I had, I think it was 8 H pluses on this side of the equation. Then you add 8 OH minuses. This makes 8 H2Os, and you add 8 OH minuses to the other side. So you're going to add, 8. So you're going to have 8 on both sides, except on the side with H pluses, it's going to cancel them out and make H2Os. You're undoubtedly going to have some H2Os on this side, so then one of them is probably going to end up being cancelled out, and you have H2Os on one of the two sides. Don't have them on both sides. You need to go through and cancel them out. Now, with this technique, really important, we assume that we are acidic unless told otherwise. So we don't use this one. We use this one here unless told otherwise. If we are told in the question that it is basic or alkaline environment, we must use this one. But if we are not told in the question anything, we don't know if it's acidic, we don't know if it's basic, we assume acidity. We assume that it is acidic, and we use the H plus method. So then moving forward, how do we apply this? Well, we apply this in galvanic cells. So galvanic cells are in everything. They produce chemical energy to electrical energy. Really important, secondary cells also have galvanic features to it, like electrolysis cells and all of that. Because remember that secondary cells have two components. They have, the discharging and the recharging. So discharging is galvanic, recharging is electrolysis. So really important that they have the two different methods in them. They're still galvanic cells. Even though they're not primary cells, they are still galvanic cells. They are still electrolytic cells. They have both components in them. So a galvanic cell, if you look at this here, this is really nicely diagrammed. This is a really nice diagram here that has all this sort of drawn out. We'll come back to it. But essentially, if you look at this here, really nicely labeled, this is a really good way of just producing a galvanic cell and drawing it out on the page. You have your two electrodes, you have your electrolytes, you have your internal circuit, or referred to as your salt bridge, you have your half cells, and you have an external circuit. So in this question here, we have SN, we have Zn solid, so zinc solid, we have copper aqueous, we have zinc aqueous, and we have copper solid. So essentially what's going to happen here is we're going to end up with zinc 2 plus in here. We're going to have Cu 2 plus in here. Now, as the equation shows already, this is going to go to here. So we're going to increase the size of this as we go on. This is going to form more copper solid. This is going to shrink, and you're going to form more Zn2 plus. Now, which of these is oxidation and which of these is reduction? Well, this goes from 0 to +2. So we've lost electrons. This is oxidation. So this here is oxidation. Being oxidation, this is the anode, and this is negative. Being reduction, over here, because we have to be opposites. Reduction, this is the cathode, and this is positive. So oxidation, anode negative, reduction, cathode positive. Now, what's even more useful with this is you need to understand which way the electrons are going to flow. So if we look at this here, which way do you think your electrons are going to flow? Well, they're going to flow from your anode to cathode. And then lastly, because I realize this has got all labels on it, I probably shouldn't be drawing all over it. Lastly, your salt bridge. Now your salt bridge, you may be given a different thing. Each teacher sort of gives a different salt bridge molecule to use. I was taught, and I keep teaching, KNO3. You're welcome to use whichever one you feel fit. But what's really important is that your cations and ions from that go to their similar charge side. So your cations go to your positive side. And why is that? Because we want to keep this as neutral as possible. We want to keep this at a sort of a neutral charge, or it doesn't necessarily need to be neutral, but whatever charge it's comfortable at. Whenever we have this Cu2 plus used up and form a solid, we lose a bit of charge. We lose a bit of positive charge. So we need to make up that positive charge by adding in more K+. They are cations. Cations go towards the cathode. Makes sense. On the other side of things, we have our anions. And our anions here are NO3 negative. Your anions in this case are going to go towards the Zn2 plus, because if you think about it, with this being oxidized, or there's a reduction in the amount of Zn solid, I should use better language. This is oxidized. You are going to gain more Zn2 plus. Gaining more Zn2 plus is going to overall make this a more positive liquid. That's like your polarity. And this Zn3 negative goes in and neutralizes a bit of that Zn2 plus. And keeps the charge comfortable. So as you can see here, anions, cations, that gets bigger, that gets smaller, or smaller than bigger, and that's essentially what you end up looking like. So if I get rid of all my scribbles, you'll be able to see this slide much better than what I sort of put down. But as you can see, this is a really good slide for showing what's going on. And it's a really good slide for showing how you should draw out one of these examples. So we can add in now an ornery cat, because anode goes with oxidation and cat goes with reduction. And you always think of the cat as happy, so that's why you have a happy cat. You have cathode being positive. So remember with the electrochemical series, you need to also understand that in redox and in especially galvanic cells, that is a spontaneous reaction. You need top, left, bottom, right. You're always going to work with your strongest oxidant and your strongest reductant. So it makes sense, because your strongest oxidant is always going to be your highest up on the left, and it's always going to be your strongest reductant is always going to be your lowest on the right. So you're always going to do spontaneous like this. So that to that. So as you've seen here, this was the galvanic cell before, but what if we did it like this? Well, you're not going to get a reaction. Why is that? Because in the electrochemical series, this is spontaneous. We're happy with that. That's what we did before. However, this one here is not spontaneous. It's bottom left to top right. Therefore, we're not going to get that nice reaction, and therefore it's not going to work like we wanted it to. And so as you can see here, this is our non-spontaneous reaction. So if the oxidant left side is above the reductant, the reaction will spontaneously occur, as you can see there. Now, what if I had two different things that could react? What if I had both Pb solid and copper solid? Well, which one is going to react? In this case here, as I said before, we're always going to work with our strongest oxidant and our strongest reductant. We discussed this before, literally like 20 seconds ago. Strongest oxidant, strongest reductant. That never changes. You're always going to use the same there. The strongest oxidant, the strongest reductant. So, strongest oxidant here, well, there's only one. It's going to be this one. Strongest reductant here is going to be this one, because it's lower on the right. And being lower on the right, this is going to be a stronger reductant. Strongest always reacts. So it's going to be these two reacting, not those two. Those two are not going to react. So, also one other thing, again, another very old meme that actually sort of describes really well. The electrochemical series is based on SLC conditions. Really important. It's based on SLC conditions. So we assume everything is at 25 degrees Celsius, 100 kilopascals, and 1 molar. Now, this isn't always necessarily true. There are some instances where this fundamentally is broken in VCE chemistry, and it's something they're not even fixing in the new study design. Kind of annoys me a little bit, but that's okay. you will find that like as these things occur, everything sort of warms up. And some of these reactions also occur with a little bit of heat as an excess. We don't discuss those things. We just sort of, for the sake and for the scope of VCE chemistry, we sort of ignore that. But if the question distinctly says that we are at a higher concentration or a different temperature, you need to make sure you discuss that the electrochemical series is not as useful. It cannot be used as a guide because it doesn't meet the constraints of how it was formed, and it was formed using hydrogen as its base. That's why that is 0 on your E naught values, and everything was compared to it with these exact conditions: 25 degrees, 100 kilopascals, and 1 molar. All of those conditions were kept exactly the same so that they would be constant variables, controlled variables. We didn't want those being confounding variables, so we made sure they were controlled. So, moving forward, fuel cells. So fuel cells are also a form of galvanic cell. They're a specific type. Really important, fuel cells cannot be, they cannot have a secondary component. Fuel cells are only of a primary, and therefore they act solely as a galvanic cell. Fuel cells are really cool because they're actually like a super useful piece of technology in terms of that they are the most efficient way of converting a fuel into energy. So what I mean by that is, remember back to sort of like, I'm using coal as an example here, like coal is not good for a fuel cell. Remember with coal that we do those like 5 steps to get it from chemical energy into sort of electrical energy, and you have your steam, you have your heat, you have your mechanical, and eventually you end up with your electrical energy. All those steps have an efficiency. They're all 30 to 40% efficient. But when you times that by 5, when you do, let's just say every single one of those is 40% efficient. So 0.4 is the amount of energy you're going to get out from what you had. If I times that 4 times, I end up with a 2.5% efficiency. That's terrible. So having 40% efficiency, 5 times, I end up with 2.5% efficiency. You don't get a lot of energy out of it. You get nothing because you're getting 40% of 40%, 40% of 40%, 40% of 40%. I actually think it should be higher than that, but I think I might have done that 4 or 5 times. I don't know. I might have done those calculations wrong. Nonetheless, you keep multiplying 0.4 by 0.4, you're going to get smaller values. This here is, it usually runs at about, I think it runs at about 60 to 70% efficiency, but you will hear people describe it as 100% efficient because we believe this is as much energy as we are ever going to be able to get out of fuels that is useful. There's always going to be a loss. There's never not going to be a loss in the energy we get out of fuels. That's reality. We're never going to be able to perfectly do it. So we think of this as like 100% of the useful energy we can get out, even though it runs at about 60, 70% efficiency. But that is amazing. That is as good as we can get. And that's why fuel cells are a great green alternative if you think of it like that. But the issue with fuel cells is that they are really expensive. They are a really technical piece of technology. And the one big downfall, which I think we'll discuss in a later slide, is they require a constant supply of fuel. So unlike our galvanic cells where we can just put it in a beaker, this one, it needs to be pumped through. So we need to be pumping the fuel through, and then it comes out. And then obviously if there's excess fuel that comes out, you can then just pump it back in. You need to keep pumping fuel through. There needs to be fuel going through. So in this one, it's a H2 gas. It's the most common one that we do. The H2 gas goes in, it hits your anode, which will be a porous anode. It'll be a new sort of a inert object. It'll be like a platinum or something, which is inert. It'll be porous. It'll hit this. And when it hits this, it may go through oxidation. And when it goes through oxidation, the H plus ions go into this electrolyte, and they push through into this cathode area. And when they're in this cathode area, they then mix with the air that's going in, which is O2, and they react and they form H2O. So this electrolyte acts as like a barrier, so there's not a direct reaction. This is still an indirect reaction, and we get that electrical circuit occurring, get the electrons moving through, but it also allows the H pluses to go through. Now, if this was actually a alkaline H2, you'd have O2 ions going this way from your O2s and other things in the environment. It's a little bit more complicated in this way. It's actually very complicated. So please don't stress about it. You're always going to work with acidic. So as you can see, this is a really good GIF that sort of just identifies what's going on. You have your H2s go in, they split, they go through, they join on with an oxygen, and then you end up with this here. Now, fuel cells, as you can see, the fuel cell is pretty much the same as a galvanic cell, except you get a continuous supply of reactants. The main difference is, this is the main difference, and in an exam, this is your first go-to. The other things that we talked about is that, as you can see here, there are subtle changes in operating temperatures. Don't worry about that. I think the most other important point is that they're really complicated pieces of technology, so they're really hard to maintain. And so therefore, that's why they're not readily used around the world. They're just not a very applicable piece of technology yet. There's also like properties of electrodes that are used. These are always going to be sort of like porous, inert electrodes rather than sort of what we're working with, like copper solid. And then sort of the role of the electrolyte. It's like the salt bridge, but it's like directly connecting the two, and acts a little bit different to your salt bridge in a sense, because it actually transports molecules across rather than just putting cations and anions in. So then we move into electrolysis very quickly. I don't want to spend too much time on this stuff just because I know it's super complicated and I'm not going to be able to teach you all of it today. This is just going to be your basics. Remember that with electrolysis, it's the opposite. So these are going to be in secondary cells. You are going to force this to occur. You're going to put a battery on there and force it. Therefore, the cathode and anode polarities are going to flip, but the cathode and anode is still going to be the site of oxidation and the site of reduction. They're not going to change. You're going to have the same electron flow, anode to cathode, and you're going to go bottom left, top right. Instead of going top left, bottom right, you're going to flip that. So as you can see here, this one here, oh no, this one doesn't actually show an example. All right, so let's just say in this sake here, we were working with nickel and zinc. We had a galvanic cell operate, and then at the end of the galvanic cells run out. You're left with this, and you're left with this. So the galvanic cells occurred, that's gone from there, and that's gone to there. Now we want to recharge it. So to recharge it, we're going to put a battery on, and we're going to force it the other way. And that works because we're now bottom left, top right. Now what's super important is if we have multiple things. So what if I also had this here? I also had aluminium ions in there. Which of these am I going to use? Am I going to use this or am I going to use this? Well, I'm still going to use this one here because it is the strongest oxidant. And I'm always going to use my strongest oxidant over my strongest reductant. And that's really, really, really important. It's actually, that's actually going to be your strongest reductant. I do apologize. I think I got my language wrong because this is, no, strongest oxidant because it's going to go through reduction. I always get those. As I said, terminology. For someone like me who's been tutoring this for many years, I still get the terminology slightly mixed up at times. Nonetheless, you're still going to use your strongest oxidant and your strongest reductant. So, there's also this concept in electrolytic cells of molten, and I hope you all know this by now. I really hope you're all on top of this. But if you're not, you need to know your water equations. So really important you know where your water equations are. You've got one here. You technically include this in your water equations. You've got one down here, and you have this one up here, although this one is although that one is less readily used. You mainly work sort of with this one here, and then sort of this one here. But as I said, your water equations are really important. You need to identify where water is. So you need to be like, all right, if I'm working with aqueous, where are my waters? So if I say I'm working with aqueous NaCl, so if I say, all right, where's my NaCl? Well, my Na, where's my Cl minus? My Cl minus is up here, and my my Na is all the way down here. Now, if I'm working with NaCl, I look for water. I also have water present. So I get rid of all of this. I say, all right, I also have water present. Where are my waters? One here and one here. Now, I'm not going to include this one because it doesn't necessarily say I have oxygen present. So that's why that one's not as useful. So what's going to react? Well, strongest oxidant, strongest reductant, going to be those two that react when I put it in an electrolytic cell. So when it's molten, they don't exist. Because I've sort of evaporated all the water out, they don't exist. And therefore, what's going to react? It's going to be these two. So what's really important is that electrolytic cells are secondary cells, so therefore they go through galvanic, and they also can be recharged. It's things like your phone, your laptop, etc. So primary cells are non-rechargeable. These are usually fuel cells, and then special galvanic cells, or just some galvanic cells. And then secondary cells have a galvanic component, and they have an electrolytic component, and they are rechargeable. As you can see, the galvanic cell is the discharge, the electrolytic cell is the recharge. They look a bit fancy like this. Please don't stress too much about them, but you can see this nice little diagram here which flips. Now, before I get into that, just quickly, when you do draw the battery in the circuit, because you will have to put the battery in the circuit yourself at times, so you are going to have to, draw out one and put the battery in, the negative stays at the negative. So important, when you sort of flip from discharge to recharge, so from galvanic to electrolytic, you flip the equations, therefore your anode, which was oxidation, becomes your cathode and reduction, but it stays negative. So it stays negative because remember the cathode becomes negative in electrolysis, so that's going to stay negative. Your battery supply, your negative side is going to point towards that negative side. So when you put in a battery, you should draw a battery like this, positive, negative. And this one here, they just put it outside. I like to put it in. But a battery has a positive and negative side. I'm sure you've seen like a AA battery before. It's the same thing. All these batteries are the same. What's really important is that that negative side points towards that negative side, which was the anode, is now the cathode, but is still negative because we flip. So important that the negative side stays towards that side and the positive side goes towards the positive side. That's a really technical thing, but you do need to do that. It does come up and you do need to know how to do that. Essentially, that is sort of the most difficult part of sort of drawing out one of these. As I said, you're probably not going to have to draw one out, but this is a really good example. As you can see, you've got anode, cathode, then it goes cathode, anode, but the negatives and the positives stay the same. And notice how the electrical circuit, as you can see, the negatives on this side, the positives on that side, it matches up with the negative and the positive. It's much like your salt bridge. Remember how your salt bridge was cations to the cathode, anions to the anode. This is very much the same sort of concept, but more in the sake of, electrolysis and all of that fun stuff. So anode, cathode, really important to understand that. So this is a really good double diagram that sort of just changes as you go through. Now, that is redox. There is way more to redox, but that is where we're going to keep it. Now, a very quick overview of organic chem. This is going to take us no more than 20 minutes, really. So this shouldn't take us more than 20 minutes, which I think we've got about 25 minutes left anyway. So we're at a good point. So this shouldn't take us more than 20 minutes, and we'll just push through this last bit of organic. Now, a lot of this is going to be the basics, again, just because I want to solidify the basics today. I don't want to be going into super detail. I just want you to be revising the sort of, as I said, the basics, the bit that's going to hold you up when you get to more difficult questions. So, really important, you need to know up to oct. Now, this is changing. This is going up to 10, but for you need to know up to 8. So you need to know meth all the way through to oct. You also need to know how to produce them in the 3 different forms. So the 3 different forms are semi-structural, right here, skeletal, and structural. So semi-structural, skeletal, and structural, they are the 3 differences. Now, you will see at times, you'll see me do it at times, you've probably seen your teacher at times, when they draw out, they're asked to draw out ethanol. And when I draw out ethanol, I do this. That's my ethanol. That in a VCAR exam is wrong. You need to put your hydrogens. You cannot just put dashes and assume they know they're going to be hydrogens. You must put hydrogens down. There must be a H, a H, a H, a H, a H. So you must put hydrogens down. Really, really important that they see that there are hydrogens there. So really important you draw those out. I know at times you'll see sort of teachers and you'll see other students do it and you may do it yourself. I do it all the time, but I'm not the one that's going to be sitting the exam in a couple of months. That's all of you. So really important you do that. Butane, pentene, oct1 ion. Skeletal, also really important. It's already sort of put on there, but every corner is a carbon unless there is something at the end. So example again, ethanol. This here is ethanol. This assumes that here there is a carbon, and here there is a carbon. You might assume, oh, there's also a carbon here, so isn't this butanol? Propanol? It's not. There's no carbon there, and that's really important. That is not a carbon. That is when there is something drawn at the end, so there's actually like a difference here. There's something going on. That is what it is. Like, so that's an oxide group coming off. But this here is ethanol. Every sort of point is a carbon. So in this one here, you've got 1, 2, 3, 4, and 5. So you've got pent, and then there is a double bond as indicated by the double line. So you've got pent-2-ene. Easy. So also you need to know how to name. Again, this should just be a revision. I'm not going to go through this slide in super detail, but remember that in terms of prefixes as well. So prefixes are sort of important in terms of that. Prefixes don't go in the order when you name. So if you have a methyl and an ethyl group, actually, that's probably not a great example. Let's just say you have an amino group and you have a chlorine group, and you cannot put them as a suffix. For some reason, you cannot put them as a suffix. You can't say amine at the end. You've got to say amino. Maybe you've already got a suffix. Maybe you've got carboxylic acid, whatever. The priority of numbering is based on the priorities of those things. So an amine group is a higher priority than a halogen. So the amine group is going to get numbered beforehand. But the naming is based on, so which one goes first out of the prefixes is based on alphabetical order. So in this case, both of amine's going to have both priorities because one, it starts with A, so it's going to have the naming priority, and an amine group is just a stronger, so 2, an amine group is just a stronger molecule. It's a higher priority, so it's going to get the numbering priority as well. But it changes with things like, if you have chloro and you have a methyl group. So that's where things change because halogens are always last. So therefore your methyl group is going to have the numbering priority, but your chloro group is going to have the naming priority because C is before N. Now, also important, if you have like dimethyl, so you might have dimethyl because you have 2 methyl groups. Important, the di doesn't count. You only think of the M. Don't think of the DI, you always think of the M, and the M is all that matters. So don't think of DI like dimethyl, think of it as just methyl. Even though you're going to write dimethyl, the M is what you think about in alphabetical order. So really important, you need to know each of these groups. So there's 8 different sort of things. You need to know your halogen groups, you need to know your alcohols, you need to know your ketones, your aldehydes, your carboxylic acid, your esters, you need to know your amines, your amides. There's also ether groups. You don't need to know them in super detail, but you do need to know what they are. Ether groups just don't have this. So they're just an oxygen in the middle. You do need to know your ether groups. They are somewhat important. They do come up. So please do know that. So going through them very quickly, alcohols or alkanols, pretty straightforward for all of you at this point. Remember what your primary, secondary, and tertiary are. Remember that primary can react all the way through to a carboxylic acid. Secondary can go through to an aldehyde, no, a ketone, sorry. And then your tertiary group cannot react. So this, as it says, affects the reactivity that occurs. So remember that primary has 1 carbon coming off it, secondary has 2, tertiary has 3. I don't know why it does that and it goes into naming. Anyway, jumping into naming, this is what I've already discussed. I don't think this is too big of a deal. What is really important to me here is this. This is the most important little diagram that we have here. As you can see, the carboxylic acid group is the highest priority no matter what. A halogen group is always the lowest priority no matter what. Everything else sort of falls in between, and you need to know this order. This is a table that you just need to know. That kind of sucks. Kind of sucks me saying it, but you just need to know this. There is no other way around it. You just need to know it. So you need to know the carboxylic acid is the priority. And it's also really important. This shouldn't say naming. This should be numbering, because this is all about numbering. This is not about naming. This is about numbering. The only aspect of numbering that this has is that the highest priority on the numbering is going to get the suffix. The suffix is the most important. People want to be a suffix. You want to be at the back. Like, this is just the reality. So the suffix is the more important. So oic acid is always going to be a suffix because it's the highest priority in numbering. So it's always going to be a suffix. Never, ever going to be a prefix. Hydroxyl, which is your alcohol, your ol, it's nearly always going to be a suffix unless there is a carboxylic acid, and in that case, it'll be hydroxy, and it'll be a prefix. So in that case, that's one of the rare cases where you end up with a prefix of your alcohols. So as I'm trying to say here, as much as it doesn't affect the naming, the only bit that it does affect is, is it a prefix or a suffix? So remember this as your different priorities. It's important you know this. So really good example here. We had this one up just before and I didn't go through it. Please have a go at this. If you have the time, please do pause and have a go. Otherwise, 3, 2, 1. Hopefully you pause and you're back. Let's go through this. So if we're going to name this, let's find how long our chain is. 1, 2, 3, 4, sorry. 4, so we're working with bute. They're all single bonds, so it's going to be butane. And now we have a carboxylic acid group. Carboxylic acid group means that's going to be carbon 1. This is going to be carbon 2. So carbon 1 is going to be bute and 1 oic acid. And at the front, it's going to be 2 hydroxy. 2 hydroxy butanoic acid. Now, really important, there are a couple of aspects to this. One, if you have two numbers, so if you have like dimethyl, you're going to write 2, 3 dimethyl, or if they're both at 2, it could be 2, 2 dimethyl, whatever it is. Numbers are segregated by commas. Numbers to letters are segregated by dashes. Important. Secondly, there is no spaces unless there is an oic acid. Oic acid is the only thing that causes a space. Otherwise, there is no spaces in your molecule. There should be no spaces at all. So even when there's like a butane 1 oic, or it goes like hydroxybutane 1 oic acid, when you read that, it reads like two ways. 2 hydroxy butane 1 oic acid, like, you know what I mean? That is, also this is wrong. I don't need to do this. Just an FYI, that was wrong. Someone's probably been screaming at the screen right now saying that is wrong. You don't need to put a 1 with butanoic acid. You never need to do a 1 with oic acid. I don't know why I did that. You never ever need to do a 1 because it's always the highest priority, so we always know where it is. So don't worry about that. But in this case here, as I'm trying to say, you need to have that sort of 2 hydroxybutanoic acid. The only space you're allowed is between oic acid. There is no other spaces anywhere else. It needs to sort of flow. So as you can see here, 2 hydroxybutanoic acid. As you can see, there's no 1 there because you don't need the 1. I don't know why I put that in. We apologize for that. Now, another one here. I want you to have a go at this. Again, please pause and have a go. 3, 2, 1. Hopefully you're all back. If we go through this, let's start out. What is the longest chain? 1, 2, 3, 4, 5, 6, 7. So it's hept. Now, there is only one functional group here, which is your ene bond at your second spot. So it's hept 2 ene. Doesn't have the name there, but it's hept 2 ene, I can guarantee it. So hopefully that's your answer there. Moving forward. So quickly as well, we're going to talk about organic reactions. We obviously are not going to go through all the other different ones. Organic reactions, the best way to learn this is to sort of write this out as like a flow chart, or like a mind map, or a poster. I find that the best way to learn this is start with a molecule and then start just reacting it and getting it to a point, and then naming what each of the reactants are. What is the reactant subs, like what is the catalyst that I needed, what was the conditions I needed, what did I add. Just, it's a really good way of sort of knowing where you started and where you end, and sort of working through that process. I think it's also good because that's the way VCAR asks their questions. You'll find that is exactly how VCAR asks their questions, and so because that's how VCAR asks their questions, that's how you should be answering them and learning them. So that's my big tip there. So Organic reactions. Let's talk about substitution reactions. So substitution reactions involve swapping out one atom or group of atoms in a molecule. Haloalkanes can be synthesized via a substitution reaction of alkanes with a halogen. So if you think of it like this, you go from that to that. The most common example is adding chlorine or chlorine gas. So you start off with an alkane, you add chlorine gas. Now what's really important is that this is lacking something. This should have heat and UV light. They are the two conditions you must have, and this is a very specific example for chlorine gas, for chlorine to be added onto an alkane. Now, you know this is substitution as well for the second point that there is a byproduct. Now, you're not going to be able to add both either. You can continue to add, but you will not be able to add both from one. Really important. If you have to just draw one off at a time, then add another Cl2 and then draw another one off. But in this one, you must write UV light, and I think and heat. I don't think it's an or heat. I'm a very big advocate of writing and heat. You need to have both on your arrow to get full marks. So you start here with ethane, you add Cl2 with a bit of UV light and some heat, and you end up with your chloroethane. Now, what's also really important about this molecule is understanding that substitution reactions generally need a catalyst more often than a addition reaction. Now, you cannot be both as well. You must be either a substitution or an addition, just an FYI. But the reason they need more of a catalyst is because these are usually saturated molecules or close to saturated molecules. And so therefore, to actually knock something off, they're fairly stable. They don't want to change. To change, they really need to be pushed, and the UV light and the heat pushes that. And as I was saying here, you can keep adding. So as you can see here, you start out with one and then you keep adding, but you must keep adding a Cl2. You can't go and add this in. That's not going to work. You need to keep adding Cl2s. And that's what goes on there. Very good. All right. So moving forward, substitution reactions with haloalkanes. These need less of a sort of catalyst. So as you can see here, to go from a Cl to an NaO2 with NaO2 to go to an alcohol, you generally just need water present. In some cases there, it's a little bit of an odd one because it's already fairly reactive now because it's changed. It's got this polarity to it, so it is happy to sort of change around. When it's a pure alkane, it's less likely to. Down here with your NH3, this is an example that comes up very rarely, but it has come up specifically before with 400 degrees and Al2O3 or aluminium is sort of what they said in one of them. So important that you understand Al2O3 and 400 degrees to go from an alcohol to an amine, sorry. So haloalkanes are like, they're a little bit more reactive than just standard alkanes. So that's one of those points we sort of brought up there. Now, addition reactions, these are a little bit different. So addition reactions, they have a double bond. So therefore, they are more likely to undergo a reaction and obtain something. They're happy to do so. So extra substituents can be added across the double bond. Really important, they must be added across the double bond. You can't add them both to one side. They have to be added across. Compared to alkanes are far more reactive, and that's due to that double bond. Unlike substitution reactions, there's no inorganic product formed. So you have no byproduct, therefore you know you've gone through an addition reaction. Now really quickly, just an example here is, this one here is a really good example. Now bromine, bromide is it's a brown molecule in terms of that when you have it as a liquid, it's a brown molecule. It's brown, the liquid is brown. When you have ethene or, whatever you've got, you might have propene, butene, whatever it is, that's a clear molecule. What's really cool is that if you don't know what you've got, you can do what is called a bromine test. And a bromine test is when you test whether the molecule is saturated. It doesn't figure out what the exact molecule is, but it tells you whether it's saturated or not. You get your unknown molecule, which it could be like, let's just say it's ethene in this sake. You don't know that though. That's clear. You put that clear molecule in a little bit of it, you pipette a little bit of it into a conical flask, and then you get a bit of bromine. And that bromine is going to be brown. And you pipette a bit of that bromine into the conical flask with the unknown molecule. Now, if it just goes in there and makes this, browny, yellowy color, and there's no change in color, like it obviously dilutes a little bit, but it's still brown, you know that molecule is saturated. However, if you put that bromine in and it goes clear, it stays completely clear, like that brown goes in, might dilute a little bit, and then it goes all clear. It means you've got an unsaturated molecule. It means you've got something like an ethene, because the bromines have then joined on like this. And when the bromines have joined on like this, the molecule goes clear. Well, this stays clear, and this disappears, because this here is still clear. So therefore, when it disappears and you lose that brown color, you can say, all right, I have a double bond in my unknown molecule because bromine has bonded to it. So that's what a bromine test is. Now, addition reactions, there's 3 types. Pretty straightforward, the naming of them. You should be able to figure it out from the names, but hydrogenation is when you add hydrogen. Halogenation, adding a halogen, and then hydration, adding water. Now, hydration is the one example you do need to know a catalyst for. It's 300 degrees in H3PO4, and it makes you an alcohol. Now, oxidation of alcohols. Requires a really strong oxidant to occur because it's something that doesn't really want to happen. So you need a really nasty oxidant. You need to remember one of these two. So you need to remember both are in acidic conditions. That's why we put H+/. And then you need to remember either dichromate or penanganate. Now, I can never say penanganate properly, so that's why I always go with dichromate. Dichromate is the one that I always write because I cannot say the other one properly. So you can choose either. It doesn't really matter. You're welcome to do either one. Don't do both. Just do one. And make sure you don't change them either. So as you note, there's 2 reactions to get to a carboxylic acid. Please do not use one here and another one there. Please don't do that. You'll probably lose marks. And I'll explain why in a second. As it says, it needs to be acidic, and oxidation occurs usually really slowly in the presence of O2. So in this one, we need to speed it up with these. Primary alcohols are the only ones that get to a carboxylic acid. Secondaries only get to a ketone. This explains why. And explaining why you use the same one is because this happens like instantaneously. It doesn't go to this and then, wait around a little bit and then go to this. It pretty much goes instantaneously. It literally goes to this and then goes to this. So therefore, saying 2 different catalysts is just a little bit silly because you're not going to, make this, take it out, and then add it into a container with the other catalyst. It's going to go from one to the other. So use the same catalyst for both. As you can see here, it goes from alcohol to a carboxylic acid. Here, it goes to a ketone. Esterification, one of our last couple of slides. Esterification is the reaction of carboxylic acids with a primary alcohol. It yields an ester. It's a condensation reaction, really important. So that means it releases H2O, and it looks a bit like this. Now, importantly, you need to have a catalyst of H2SO4. You either need to write concentrated H2SO4 or H2SO4 liquid. Both are acceptable. This is wrong. It says generally avoid. This is just wrong because if there is water present, it changes how the reaction occurs because you want water sort of produced because when water is produced, you have the reaction occurring. If there's already water there, think of it like equilibrium yield sort of thing. If you already have water, it's not going to want to go forward. It's going to be like, well, why would I want to go forward? There's already water there. Like, it's one of those things. And there's more to it as well, but that's sort of one of the explanations. So really important you understand that when there's water, there's water present, you don't, it doesn't really work very well. So therefore, you need to write either concentrated or liquid form of H2SO4. And also really important in the naming. So remember that it goes IL O8. So IL O8. The IL is the alcohol or alkanol, and that's a terrible alkanol. And the O8 is the carboxylic acid. So if I had, in this case, I have ethanol. This is ethanol, and this is propanoic acid. This is going to be ethyl. Now, really important, the alcohol drops the ane-ene ion. Now, you are only ever going to work with ane alcohols. So alkane alcohols, you're only ever going to work with them for the production of an ester. So don't stress about, what if it was an ene, what if it was an ine, not going to happen. Ethyl, and then prop, and you keep this, propanoate, because in some cases there will be a double bond and so forth in the carboxylic acid side of things. And so in those cases, you're expected to sort of add it. But it will never be in the alcohol, don't stress about that. But in this case here, it's ethyl propanoate. So, as I said before, reaction pathways are the best way of learning this because that's how they ask the questions. VCAR asks questions in a reaction pathway sort of form. They start with a molecule and they have a whole bunch of boxes and they have a little bit of information in each box, but you've got to sort of add the rest of the information. They sort of talk you through it in a stepwise manner. So don't stress, they don't just throw it at you and go, figure it out. They do sort of walk you through it. But it's sort of like this. It's sort of like you're going through all of your steps and you go from, you start with an alkane, you go to a haloalkane, you have your HCl come out, then you go to an Na, you go to an alkanol. That alkanol has nothing come out because remember this is it should actually have something come out. Sorry, that's a lie. It should have NaCl come out. NaCl will come out because it is a substitution reaction. Then you go down to your carboxylic acid. This is oxidation, so we don't really worry what sort of comes out. Don't stress about that. It's not something we discuss when we talk about oxidation. And then here, there should be a H2O coming out of here because this is a condensation esterification reaction, and that forms your ester. And so this is an example of what it looks like. As I said, it sort of talks you through it and shows you how to go about it, but it does sort of say like, hey, A, identify this. B, in the appropriate box, put this. C, give the names. So it does talk you through it. And this is an example from 2013, but they use the exact same format now. Otherwise, that is everything for today. I believe we're about on time, maybe 1 or 2 minutes early, but that's okay. Thank you for today. Thank you for putting up. Sorry about the little technical issues at the start. Otherwise, good luck. The chat is there. If you have any questions about today, please look through that chat. That chat will be there as much as it won't be active. You can look through that chat and find any of the questions you have will probably already been asked. They're probably pretty common questions, so I probably will have already answered them. Please feel free to look through that. Otherwise, go and enjoy the rest of your day, and I will see you around. Good luck with the exam.